So, where this all started? Well, darker story. I had set up an ElasticSearch cluster. That was a test cluster, single node, with Cabana. I was feeding data of events in Elasticsearch. You will know that this is one of the situations where you can start panicking, because this means that you're producing more data than your cluster can process at a time. AKA bulk retention, particularly when using ElasticSearch or beats. Now, what happened? Well, I started more data, so I was like, okay, let's pre-process the logs with ElasticSearch. So I'll add more stuff into that. And well, I want metrics with that, sure. Let's throw those in, and well, while that gives me a pretty good image of what's going on with my stack, I needed something more, which was the things that my applications were not logging. Well, packet beat, perfect, right? I'll grab the messages going back and forth. And then it died horribly. It turns out that there never so now, of course, what I tried then was improve the performance, and I made a lot of mistakes, which I'm going to go over here now. And so the next section is like how to really ruin the performance of your cluster. We'll start with the simple ones, so the things that are not as bad in the general picture. Yeah, so that was the setting that I had. So like again, single node that was master. I had the data. I had Cabana. I had log/, feeding it. I had, of course, beats. Lots of beats feeding it. It was supposed to be temporary. It was supposed to be so users can say, okay, I'm familiar with Elasticsearch. I can start building my dashboards. But of course, there's nothing as permanent as a temporary solution. So they wanted it. And once I started fixing it, I'm sure at some point the Elasticsearch engineer was like, something's wrong. All right. So things that an experienced Elasticsearch admin shouldn't do. But if you've used Elasticsearch in a production environment, you might have been guilty of these at one point or another. These are more or less passive. They're since by inaction. They can be forgiven. But there are also things that require fairly technical knowledge about how the Elastic Stack works to understand why they're wrong. Trusting the default index templates. Well, the default templates are great if you just want to shove raw data into it. But really, you don't need to index all of the fields, which is one of the defaults. You don't necessarily want everything to be a keyword or a text field. So that there's some work that can be done there. You can very easily have way too many shards in your cluster. Part of the default here is with the default in Elasticsearch that the index has 5 shards. There's actually, correct me if I'm wrong, Maya, discussion within Elasticsearch about, within the Elastic company about reducing the default in future releases. So is it 3 or 1 shard? Or just 1 shard, yeah. And then, like many of us who deal with hardware, we look at IOPS as we can look at IOPS as the only performance metric. But with Elasticsearch in particular, especially with Ingest, you also want to look at latency because of the way the transaction log works. We'll cover that later. Now, I mentioned log/, so this is a little bit of a digression here because it's not Elastic specifically, but or Elasticsearch specifically, but it falls under the Elastic umbrella. You really shouldn't be trusting the input to be same, especially if you know your developers. Valid JSON is not necessarily good JSON, so if the field foo has the string 2, Well, you might need to convert it to ternary. Even if the JSON is valid and is correct, sometimes, depending on how your data is presented to log/, might end up indexing the field through as a keyword. At least this was my experience with previous versions of log/. Recently, I can't really talk about that because now I learned my lesson and I've worked on my index templates. But I also run into issue where I implemented very large grok patterns for my, for example, HTTP access logs or my database flow logs. And what happened is that I was shipping those logs via syslog server to another location where log/, was picking them up. The problem was that the syslog server was was using strict RC standards and was truncating the logs. So suddenly my really big, nice grok pattern that could parse a full line couldn't parse it because halfway through the user agent was cut off and everything after that didn't match anymore. So you want to check that. And another issue that you might run into log/, is single-threaded filters. Probably the most used and abused one would be the DNS filter. So if you have an IP, you want to look up the host name so that you can ship those together. That's enriching your data, right? Or vice versa. But there are several other ones. I believe ZeroQ is also single-threaded. A couple of ones where, again, we're doing an external lookup, you're enriching the data, but those are single-threaded, which means that if you're running log/ on an 8-core machine, you're still only using 1 core at a time for that. So that's the reason why I bring this up, tied together with the previous slide, is that I want to emphasize the importance of knowing your data. You want to really model your data. You want to know, okay, like this is what I'm putting into ElasticSearch. If you're just throwing in raw logs, single field that's just text, fine. You don't need that. But once you start analyzing, once you start splitting it out, you want to make sure that you use the right tools for that. Now, here's where things got really bad. Of course, so the previous mistakes with ElasticSearch, those were understandable. Like, if you don't know that you need to change them, then you can't change them. But if you start focusing specifically on the error that you're seeing, you can get yourself in the rut pretty quickly. So a panic admin should not assign too much RAM to the JVM, and this is a very easy mistake to make because, hey, I have a 32 gig machine, and well, I read on the Elastic documentation that the ideal heap size for Elasticsearch is around 30 gig. Yeah, sure, let's assign that. The problem with that is that you don't leave enough memory for your file system buffers, which will kill your write performance. The suggested size of the JVM is generally recommended to be about half of your RAM, and no more than 30 gigs. Now, well, you get the 429 error. You say, okay, you look at related information and says, okay, the queue is full. Let's make the queue bigger, right? Right? No, don't do that. The only thing that you'll end up doing is just delaying the problem by half a millisecond. Because at the rate at which you're throwing messages on your Elasticsearch cluster, that queue will fill up again. And then you're back to the same problem. Another common thing is like, okay, I see garbage collection happening for 10 seconds here. Let me change the garbage collection. G1, GC, that's great, right? Slow garbage collection times. Don't do that. This is typically one of the situations where Elasticsearch runs into really, really strange behavior. To the point, actually, that with recent Elasticsearch releases, if you run it in production mode, which a production Elasticsearch cluster is one that where the where the interface is bound to anything but localhost. When that happens, when Elasticsearch starts in production mode, you will actually run a bootstrap check. And one of the things it does is check for G1GC. So this is something that was so common that they actually made a check specifically for this. Which fortunately also means that if you run things in production mode, it will explicitly tell you not to do it. But if you run it as a test cluster, localhost, then you only get a warning, and if you don't look at the logs, well, you don't know what's going on there. The other thing that you shouldn't do is increase the thread pool size. Why is that? Well, by default, Elasticsearch will create a thread pool of that is equal to the number of cores on your system plus 1. I don't know what a plus 1 is, but it happens. Now, you're thinking, well, the thread pool is what's consuming from the ingest queue, so more threads should be better, right? Except that it really isn't, because you have to also consider concurrency there. If you have more threads than you have cores, then your scheduler will go crazy trying to switch back and forth between threads. You lose performance. More importantly, though, if you're running on, if you're not running on SSDs on spinning Rust, the more threads you have writing, the more your hard drive headers to disk, and that's even worse. You absolutely kill your performance. So don't. So actually, one of the recommendations, if you're spinning Rust, like non-SSD hard drives, is to decrease the size of the thread pool. And most importantly, or maybe not most importantly, but definitely something that you should not do, is arbitrarily add another master. Right? One node, okay, has this performance, and you might think 2 nodes double the performance. No. You end up in a situation where if one of the nodes goes down, you're suddenly in a split head situation, or the entire cluster suddenly has, if you require 2 masters, then you have no redundancy there. And even worse if you put them both on the same hardware, on spinning hard drives. So yeah, these are things that I shamefully admit I did in a panic. But there are also things that that highlight the particular bottlenecks of Elasticsearch when it comes to high volume ingestion. And if you made the similar mistakes in the past, my condolences go to you, but you're not alone. So ultimately the result was a train wreck, but I learned a lot from that, specifically regarding optimizations. I learned how to optimize my indexes, I learned how to optimize my storage, and I learned how to plan my cluster. Each of these steps required, to some degree, knowledge of my data. So again, going back to what I said before, know your data. If you don't know your data, you will possibly make mistakes and not do much to increase your performance. So with regards to order of these, optimizing indexes is easier to implement in regards that you don't need any external resources. This is all about data modeling. So you don't need to get an extra server to optimize your index. To optimizing your storage, particularly if your storage is still fairly low, like if you're in spinning Rust, you have no SSDs. This is a fairly cheap optimization that can make quite a big dent in how your cluster performs. A good kind of dent. And lastly, like eventually at some point, there's so much optimization that you could have done with your indexes and your storage. I need to start thinking about growing a cluster. Do I want to grow it vertically? Do I want to grow it horizontally? And then we'll go a little bit over that. So with regards to index optimization, there's the 3 more common steps are adjusting the number of shards, particularly for hot indexes. So indexes that where you're actually writing into them, you want more shards because that means that you can have some writing here, some writing there, some writing there, and spread out the load. But then for your warm indexes, so if it's a time series data, your yesterday's log is not going to get written to again. So you want less indexes for that because you want less shards for that because the more shards you have, the more threads you have. The more threads you have, the more I/O you have, the more memory overhead you have. So that leaves less room for the important stuff. And contrary to popular assumption, the shards can be quite big. The recommended shard size these days is somewhere between, well, depending on who you ask, some will say 10 to 40 gigs, or some will say 15 to 55 gigs. But still, more or less, it gives you an idea of the range there. More importantly, your shard can be bigger than your heap size. You don't need to keep your shard size down because you are only running on 60 gigs of RAM. Reducing the number of replicas for ingest in particular is also important because the way that the cluster works is when you receive a document to index, it gets sent to each replica to be indexed separately. It does not get first written to the master and then just copied out. So the more replicas you have, the more you're duplicating the work when you're indexing. And lastly, as I said before, plan your index templates. It can be something as simple as changing the field type, but you can also do a couple more interesting things, like just disabling indexing for some fields that you know are just ancillary data. Like one thing that I have a habit of doing because I'm a hoarder with regards to data is that I parse out my my field into, or my event into all of the different fields that I'm interested in, but I also throw in the raw field because who knows, maybe I missed something. Well, I don't need to index the raw field because I'm never going to query it. So that saves you a lot of performance doing that. Now, again, with regards to the number of shards here, we can, if we look at the red indexes, or the red index, that's the hot one, it has, in this case, 3 shards, and then as time goes by, it will turn into a warm index by nature of not getting written anymore. What we can do is is anyone here familiar with a tool called Curator? Okay, so a couple of nodding faces here. Curator is a wonderful tool. It is the recommended way with which you should run your index maintenance. So you can run it on a daily basis or however frequently you want. But you can set up rules and say, okay, if this index is is older than X number of days, let's say 3 days, just to be sure, let's shrink it. That's shrinking is done via the ElasticSearch API, which basically takes all the shards and compresses them into however shard number you want. In this case, I'm shrinking it to 1 shard, but you can choose 2, etc. There happens also to be an opposite type of API, that split API, which, as you might have guessed, takes your indices and splits them out into more. But again, this is a process that you should look into automating, and it will improve the bottom line of your cluster performance. Second step, number of replicas. Let's say I have 3 nodes here on each one, and I have 2 or more indices. In this case, I wrote 2. And as I'm ingesting data, I write them to each of these indices. Now, if I have 2 replicas, it means that every document that I'm writing here, no matter what index it's in, I'll tell me that each index has 2 replicas. Every document creates work on all of my nodes. And just by reducing it to 1 replica, I can cut the work down to 2/3 of the original, which is quite significantly, especially when one new cluster cannot keep up. Of course, if you don't need to stop at 1 replica. If your data is not absolutely 100% necessary to do this, or if the survival of your data is not 100% necessary, let's say worst thing happens, your node dies, you lose a day's worth of metrics. Is it the end of the world? Not necessarily, but that means then that you can have 0 replicas, and then have your ingest a lot better, and then go back to, let's say, your historical data, like, or once you're fairly certain you're not writing the index anymore, or at least once you know that the worst has gone by, you can go to your Curelet tools that will say, hey, change the yesterday's or any index that's older than 24 hours, change it to have 1 or more replicas. And when you do that, it costs you very little. I mean, it's copying the data over once, but now you have your redundancy, and your historical data is safe. When it comes to storage optimization, there are a couple of rules that are fairly well set. Like if you look at the ElasticSearch website, there's several pages where they basically go over exactly these steps. But what you want to do in terms of bad for a buck, SSDs. Like if you can parallelize your writes, you will get the best performance out there. Now, everything else being equal, local storage is better than network storage. The reason for this is the transaction log. So every time you write your documents to an index, they don't just get written straight to disk. They get buffered. This buffer gets synced to your disk every once in a while. And after the buffer is full, it gets written out to your Lucene segments. So you have several writes happening. Some of these, particularly the transaction log flushing, which is this buffer here, this needs to happen very fast, because as long as the transaction log is being written to disk, nothing else is happening as far as ingest is concerned, because it's blocking that. So while SSDs are a good improvement, you don't just want to put everything. Let's say I have an NFS appliance that's backed by SSDs, but the latency is 100 milliseconds. That's horrible. Don't do that. You're probably better off with a single thread with local storage. The other thing also is you do not need RAID 10 or RAID 5. You can use RAID 0. You can use a RAID 0 of 5 spinning disks, which is better than if you were doing, say, RAID 10 of those 5 disks, like 4 disks plus a hot spare. Particularly when you're running an HD cluster in Elasticsearch, because Elasticsearch will take care of the redundancy then across different machines. Your single machine does not need to be a point of failure. So you can try to squeeze as much hardware performance out of it as you can. You can use commodity hardware too. Like again, we're talking about budget here. Maybe your Ingest server is just a desktop with a off-the-shelf SSD. That's of course not ideal, but when you need to justify your purchases, well, a $2,000 machine that just sits in a corner is a lot easier to justify to your CFO than a $15 or $20 $15,000 or $20,000 server that ultimately the only thing that it gives you is guarantees the data on that server itself. But if you have the redundancy cluster-wide, you can kind of fudge that. Again, going back to index thread pool, you can if you're using spinning hard drives, you can reduce the number of threads. By doing that, you have less concurrent writes, which again improves your performance. Now, I did say that you should not increase the queue size for Ingest, but you want to increase the buffer size. And I'll have a slide later that explains why this is not the same as the queue size. But ultimately, it boils down to like how often things get written down. And then there's only things that you can do to tune your I/O scheduler, like the default I/O scheduler, the completely fair. I don't remember what the Q is for, but CFQ. That one is tuned for hard drives. It makes sure that each thread gets a fair slice to write the disk. But for SSDs, you don't need that. You can use no-op, which just first in, first out, or deadline, which says, okay, like these processes need to have written down within this time window. For SSDs, that's fine. You can parallelize them. And you also want to look at your file systems. Now, depending on your hardware, you might choose different things. If you have spare memory, let's say you have a 128 gig machine, and you want to run ElasticSearch in it. Well, you're not going to use all those 128 gigs for ElasticSearch. You're probably going to use 30 gigs, maybe 31 if you want to squeeze it. Which leaves you with a lot. ZFS is rather memory hungry, but it gives you some good features that you can make use of, particularly when you have hybrid hardware. You can run almost everything on spinning hard drives, like your volume, for your hot indexes. But you can put your ZFS intent log or your L2ARC on an SSD, and these are effectively buffers. They act very similar to the Elasticsearch thread pool on the buffers, in that it caches the writes. Then the log says, okay, I intend to write this to the final destination, but it treats your SSD as a cache, and you can choose how big you want that one to be. And again, because you don't need redundancy, if it dies, well, I mean, you might need to put a new SSD there. You might have some temporary lost redundancy, but ultimately it's not so bad. You also get compression, which I mean, it can be a mixed blessing. Like maybe you don't want to compress things that you ingest right away, but generally it's not hurtful in my experience. On the other hand, if you only have 16 gigs of RAM, and of course, if you have only 32 gigs of RAM, let's have something more realistic for production size. Okay, your Elasticsearch heap is 16 gigs, and that leaves you with, probably after all of the OS caches, everything else, with something around 10 gigs of RAM for your file system. That's not a lot. You might want to end up using ext4 or something similar, XFS. So again, you need to know your data, you need to know your systems. Your performance comes out when you put those two together. Going back to the thread pool, like this is a quick little graph here that gives you an idea. Okay, if I have a single thread, the writes will happen sequentially. But if I have two threads, well, they might end up trying to write in different places at the same time. With SSDs, your performance is going to be the same on each one of these, at least per write. But with spinning hard drives, your head again will start going back and forth. So imagine doing this with 10 or 20 threads. You get pretty bad performance there. your ingest buffer size, this slide I mentioned before, again, as the documents get written into your buffer, in this case I have two different buffers, one with a size of 3, one with a size of 6. Once the buffer gets full, this gets flushed to a Lucene segment. And the Lucene segment is one of the units inside your shards. And the buffer gets empty. When it's full again, you get another flush. And each flush creates a new segment. And it's another write operation. Now, ultimately, whether you have a buffer of size 3 and a buffer of size 6, at the very end, whether it's with 2 segments here or 1 segment there, the amount of data you write is the same. But in this case, you do half the writes. You do a bigger write like for every 2 writes that you do here. This might not seem like a lot, but again, when your bottleneck is your I/O, your file system, this can make a big difference. And again, going forward, cluster architecture. Once you tuned your indexes, once you tuned your storage, you're gonna have to start thinking about growing out. You want to maybe look at dedicated master and data nodes, so that you have separate threads for controlling your cluster and for indexing your data. Particularly when per node CPU is at a premium, this is something that can increase performance. More importantly, once you have separated your masters from your data nodes, you can start growing your data node pool while keeping your master cluster, your masters at an ideal number. You might want to do index routing again, as before, like hot warm nodes. Like, okay, I have like similar to before. Like, okay, I want to index to where the indexing happen where the SSDs are, but once I've indexed it, and once I know that I'm not writing to this index anymore, I can shove it off to some other node that has spinning hard drives. They're cheaper, right? And as long as you don't need the absolute best search performance, it's good enough. You can do this with Curator. Again, Curator is a wonderful tool. You can as I said, you can delegate redundancy to the cluster itself. You don't need to have fully redundant hard drives. You don't need to have redundant power supplies. You don't need to have server hardware even. You can do this with commodity desktop machines if you need. And lastly, you can start looking at more clusters. Going back to my initial scenario, okay? Turns out that what I was writing in from packet beat was about 90% of the volume of my ingest. It means that I can create a new cluster just for packet beat, and then keep all of the other indexes in my old cluster, which was working fine without this big massive one. So you can start thinking about how to scale it up that way. And there's features like cross-cluster search. You don't need by splitting your data into multiple clusters, you're not isolating the data from each other. So keep that in mind. Again, going back to the dedicated master data nodes. In my opinion, this is the recommended upgrade path. So you start with we'll probably start with your single node where you're testing stuff. You want to grow it out at least 3 masters. And at that point, well, you have 3 nodes, so you might as well have them all data nodes. Although, if you don't have enough resources to have 3 data nodes, you can have 2 data nodes and one that's just a master. That's fine. As long as you have your 3 masters, you want to keep that core up there. And then once you grow it out, okay, have dedicated data nodes. You can grow that horizontally. You can have as many data nodes as your cluster reasonably supports. I mean, of course, you don't want 100 data nodes with 1 gig each, but you also don't want one data node with 128 gigs. Maybe you want 6 with 16 to 32 gigs of RAM and reasonable storage. Setting up closed cluster search is really easy. Yeah. All that you need to do is set up this. The Cs will disappointing to the transport of your remote clusters. And then when you're querying, you just need to prepend the cluster name to your index. So it's cluster:index. And that's it. You can do cross-cluster search really easy like that. So it's a lot less daunting than it seems initially. Going back to index routing here, again, Curator can take your indices that are cooling down, your warm indexes. You can automatically put them onto your warm nodes. You can keep your SSD here. You can have terabytes, petabytes of data here. Still have decent index performance by knowing that your indexing happens on the fast storage there. And of course, you don't have to take my word for it. You can measure these changes yourself. There's a couple of easy ways to do it. The easiest by far, or at least the simplest by far, is set up your cluster, start writing to it. Then open up the firehose. Or at least do it gradually until you start getting 429s. That's your baseline. You say, okay, I can index 10,000 events per minute. Make your change, edit your cluster. And then do your test again. And then now, okay, like you made a little change, like you changed your index buffer size. And now you can write 11,000 events per minute. That's 10% improvement. That's not bad. But there's another tool that came up fairly recently. It's called Rally. This is by Elastic. It's a benchmarking tool. The nice thing about this is that if you just got the hardware, you haven't even installed ElasticSearch, you can run Rally against it. It will provision ElasticSearch to run against it. Really, all that Rally needs is Python 3, Git, and the JVM. It will take care of the rest. You can tune it. You can configure it to run tests against multiple machines at the same time, and it will give you the report. It will tell you, okay, this is how these perform. This is how those perform. You can compare and contrast right there and then. Yeah, and that is the end of my talk.
Next time we get the presentation with the meeting.
I will share it with the meetup tonight. I'll even add some references, some pages that where we can get most of the excellent information.
So I got a question for you. Did you find that packet beat gave you much value versus, for example, a time series database like Prometheus, Grafana, and just using that as the performance measurement? It uses a lot of the PSYOPs, but it's not quite the same data. But
well, yeah. So all the time series databases, you still need to feed them your network capture. So packet beat, what it does is...
No, I'm saying that would be more like a scraping approach. Like Prometheus scrapes the metrics out of the application,
yeah,
but it also is stored in a time series database, so it has a lot less PSYOPs needed. It doesn't give you the same data, but...
Yeah. Okay, so...
I guess what I'm asking, did you find packet beat, people were searching the results that only came from that? And were they doing it only because it was there, or they were doing it because they needed it?
People weren't searching packet beat at all because packet beat was killing everything.
So you
I couldn't get even that far.
Right.
But metric beat
yeah.
Was giving us very, very, very good information. We're running metric beat in production. when we do incident response, is one of the tools that we go to use.
So why would you use metric beat into Elastic versus a time series database is maybe the question I was asking. There's a lot less IOPS for the same data.
Familiarity. If you already have your other logs in ElasticSearch, metric beat you will have all your data in one place. You can correlate it. If you don't, I mean, you can use whatever you want. I like ElasticSearch, which is why we'll continue using metric beat and we'll continue using everything else. But if you'd rather use Prometheus, if it meets your needs, I'm not going to.
It's just
try to
something
convince
like
you otherwise.
it's just something like it's like 10,000 times more efficient for the thing that it's optimized for, right? So if what you have is truly just time series data, it's to match quite a bit more efficient.
Prometheus has some scalability issues though, like on the massive side of things. If you're running microservices on a fairly small cluster, it's probably enough for you. But yeah, high availability in Prometheus is not a fine and not a first-class citizen. ElasticSearch it is. So if you need to keep your data, if you need to reference it a year from now, ElasticSearch might be a better choice because you can not only put it in ElasticSearch, but you can also work on it. You can, let's say I have my metrics. I collect them every 5 seconds. Well, after a month, I might not need 5 seconds or another. I might need 5 minutes. I can do a roll-up in ElasticSearch. After a year, I can maybe do hourly roll-ups. I can still keep the data. I can shrink it though. I wouldn't know how to do it in Prometheus. I'm not saying it's not possible.
It does it natively in Prometheus. That's what it's designed for. That's why it's so much more efficient for that narrow type of data.
Yeah. But again, like metrics is not the only thing that ElasticSearch does.
Sure.
In our case, like in our case, metrics is one of the tools that we use, but the logs are our first class.
Yeah, that's what it's optimized for.
Yeah, based on my experience, what we found is that all of the stuff in the presentation is great, but it took you how long? A year, 2, 3 to figure it out.
These are mistakes that I made over 3 years. Like I fudged the scenario a little bit. Like not everything happened all at the same time, but over 3 years I ran into all of these.
And the problem is that every big data store would have probably the same set of issues that you would have to figure out.
Absolutely,
So the
yeah.
operational complexity in many cases just doesn't justify.
A lot of the mistakes I made are because I was used to RDBMS, and I tried to fix ElasticSearch like I would have fixed an RDBMS, and it's not. A lot of these things are completely. You want to look into the opposite
The
direction.
data structures themselves are different.
That's true. That too, yeah. And honestly, it wasn't until about a month ago that I really understand some of the more intricate things, like things like the index buffer. Why it's important to reduce the latency. I'm not an ElasticSearch drill, but I took the Elastic Engineering 2 course, and that's where I learned about why it's important to do this. It took me 3 years, but I know it now, and I want to spread that knowledge.
The issue is that every single new system you deploy will require some amount of operational complexity and overhead.
Absolutely.
If you store this much data, it will require significant investment to keep managing.
Yeah. And another mistake I made is that I didn't go to the community first. I tried to figure this out by myself. But the community it's really great. Like of course, again, like the bootstrap check, like for G1GC. These are kind of mistakes that are surprisingly common. Not because ElasticSearch is bad, it's because if someone goes into ElasticSearch with knowledge that is not Elastic specific, you end up working based on what you knew before. which doesn't necessarily correlate, right?
You mentioned your big dictionary of grok. So I'm finding that that's a lot of work, and everybody is always mad about the dictionary of grok, all the regexes. You know, you've got we have the problem that multiple languages each output the same thing differently. Like Node.js and Python, you know, they log it differently. And if you're ever going to want to compare a URI, one of them calls it one thing, one calls it another. So your first thinking is, okay, well, I'll just make all that normalized with my magic regex patterns. And then after you've gone blind for the day by looking at backslash, curly, square bracket, and so on,
Yeah.
and then there's a version issue, and now you've got different versions of the regexes. Are you going to continue to go down that path, and do you think it's going to get you where you want to be, or are you going to change all the source to log in JSON?
I kind of still need to, because what I'm doing is I like to enhance my data as close to the source as possible. Like for example, I use HA proxy in one of our deployments, and I don't use the default HA proxy log.
Right.
I add, off the top of my head, about somewhere between 6 and 10 headers to the log, which means that I can't use the default grok pattern anymore. I need to write my own. And I find that.
But do you ever have to cross-correlate a field that you generated from HA proxy with one from Node or Python or something?
Yes.
And as a consequence, have you calibrated the regexes so they call the same field the same thing?
Yes.
Okay.
And over those 3 years.
And
yes.
how are you keeping that in sync?
Ultimately, trial and error. That's how it started for me.
Right.
So what I found is that in the test cluster, I would run into collisions of field types, because like, okay, from one source this field was an integer, and from the other source it was a keyword, and then Elasticsearch didn't let me index those together. So I started splitting the sources into different indexes, and going back to the like too many shards thing.
Yeah,
That's how I got to too many shards.
Yeah, it doesn't work.
Like I was having about a good dozen or so indexes, each one with each index with 5 shards, each one a time series database. So times 30 after over a month, I had over 1,000 indexes. Oh, so over 1,000 shards.
Right.
So here's the thing about data and Elasticsearch. Like, it's really recommended to denormalize it first. So even though I was killing my performance, it's still the right approach. I split it out. I took a look at each of the indexes individually and said, okay, I want this. This is always the same data. This is always correlated. Let's name them all the same, and then make sure that they're the same field type as well, by creating my index templates, and then start putting them into the same index. I don't necessarily need to. If I wanted to, I could have gone the other way around with my suggestion, which is using different clusters and doing a cluster search. That would also work.
Do you have anything that logs directly in JSON format without going through the groks?
Yes.
Do you find any of them have collisions that are impossible to deal with? So as an example, I ran into one where one thing logged something as an object and the other logged it as a key. And you can't do that.
I did run into those. Again, with your index templates, you can make sure that they are massaged into the same field type. But
how do you do it if one of them's an object?
But
and one
a
of them's
more
not?
interesting problem that I ran into was that this was my previous company. We were logging. They were logging JSON, but they were logging it. They were reversing the key and the value.
Really?
Yeah. So I ended up having.
On purpose?
It was. I mean, I won't say on purpose, but like it just happened to happen. Like that. But it turned out then that I
And how big was that index?
1,000, 2,000 different fields,
Yeah.
each one showing up once or twice.
Yes.
That also killed my performance.
Yes.
So I think, again, going back, you need to know your data.
Uh-huh.
But that was easy for me to denormalize. I just inverted that or turned it into an array.
What may be helpful, there's a huge effort in Elastic, it's been running for a year now. The project is called Elastic Common Schema. So the idea is that all of the products within Elastic Stack are going to use the same schema for naming and stuff. So
Yeah.
there's a huge dictionary of this is how you're supposed to call a request IP. That's the request something else, and that's the user agent.
So is there a package I can get for like Node Express or Flask or Django to
I
output it that way?
I would,
Because that's kind of what I need, right?
I don't really know. So I know that the products themselves are going to use it, and the idea was that customers can look at it like when you build your group expressions.
Yeah.
You can look at that dictionary and say, I need a name for a field that will
Okay.
hold the remote AP of a connection. And you go and look at it, and it's designed to work with like IDSs, all kinds of firewalls. So the idea is that it will be compatible with third-party
Yeah.
services and systems.
So
I think maybe we can take this offline.
One more question about duplicating. Have you experienced with? Have you, for example, in my case, we've got a lot of ingested logs duplicated few times, and I know today how to prevent it. I'm using fingerprint, but I still thinking about how I'm removing it from my indexes and how I'm cleaning all this up. So
Is
what I'm
this
thinking
duplication
is
happening at the
reread
source?
the
Or
index again and send it through the same log stash that I have.
is this duplication happening at the source, or you did just happen
On the
to see
source.
duplication?
So it's filed with the same few times, for example, the same log, or if it's server, or if server itself has duplicate message, exactly the same message, exactly the same time, exactly the same event, so you get it multiple times in index, you get it multiple times in logstash. So today I'm preventing it with fingerprint. So fingerprint hashing doing the hash of message field and getting some ID. So I'm rewriting the event again and again with the same ID.
Yeah.
But before it was a unique ID and created.
But yeah, the fingerprinting is what we do too. Not necessarily, not specifically that scenario, but we have a database which we are loading into ElasticSearch to do correlation. And of course, we now have multiple logstash instances that read the same database, but the offset from which to read is stored locally in logstash. So the way we prevent duplication is with fingerprinting as well. But that reminds me also of a scenario that I ran into a couple of years back. Because of the 429s, or actually not because of 429s, because of the problem I had with the graph patterns where logs were truncated, ElasticSearch would reject the bulk index. And this was, I think, logstash 5.x. And logstash will try to reinsert the entire 1,000 messages again and again and again.
Yeah.
So we ended up having nothing, and then big spike, and it kept piling up. Nothing new after that because logstash kept getting stuck in a loop there. I haven't experienced that again lately, partially because I'm sanitizing my data, probably also because that finally got fixed in logstash. But it was actually now logstash has the failure queue, so it removes those messages out.
It now can do a partial retry of the log. So
Yeah.
it tries to index it, gets the response back, and only retries whatever it could.
Yeah. But if you're still running on an older cluster, you might run into this.
Okay, next time you said that we should know our data, right? So you said you should know your data. You should
Yep.
know your data, the data you're working with. So how do you your data? How does that take to know the kind of data? If that's a huge data.
Yeah. Small baby steps, really. That's how I did it. I started out by treating ElasticSearch like a kitchen sink. I was throwing everything into it. A lot of it, I asked initially, was unparsed. I was just like, okay, let's just store it for later. But of the things that I needed to enhance, that I needed to where I needed to do correlation, where I needed to do set up my dashboards. Really, like, all I can say is try to be meticulous. Look at your data. Look at your edge cases. Make sure that you do your error checking in the pre-processing. Denormalize your data. And do the enrichment beforehand. Don't try to correlate things inside ElasticSearch if you can. So if you have your event message and you know that it needs data from a different system, try to get it right away and enhance it there in ElasticSearch or in your ingest queue if you can, or even before that on your application, so that you don't need to modify data once it's inside ElasticSearch. You can do it, but it's going to be much more work.
I think we will finish with this presentation. Thanks very much, Klaus. It was I'm going to get several minutes of break while I take a setting up this presentation.